Section 1.8 introduces linear transformations. This is perhaps one of the most important sections that we'll cover really in the course, with the fact that linear transformations are really useful mathematical objects, and transformations in general are used constantly throughout math, physics, and science, and linear transformations are a really special, a really important special case of that. So let's first mention what a transformation is. From Rn to Rm is a rule that assigns to each vector x in Rn a vector t of x, we'll call it, in Rm. So we're going from n-dimensional real space into m-dimensional real space via this transformation t. So that could be something like R2 to R4, or maybe R5 to R1, whatever it might be. Now you'll notice that this definition is really not much different than the definition of a function, right? A function takes an object from one space and maps it into another space. And really, it isn't much different, but we tend to talk about mappings from real vector spaces as transformations, or functions as mappings or transformations. So just as with functions, the domain of t is the function from which we're mapping. So Rn in this case, we're picking up objects in Rn, plugging them into the transformation t, and it's giving us out a value in Rm, which is the range. So elements that we map from are the domain, and elements or the set of elements we map from is the domain, and the set of elements we map to is the range. This is often written like this: t from in to Rm. So domain and range. There is one subtle point in here I guess I should be clear about. The codomain, Rm is not necessarily the range unless t happens to cover the entire range. We'll talk about what that means in a later section, but this is actually domain and codomain. So domain and codomain. So if we think about it, we could have a simple situation where maybe Rn maps an element, or t maps an element in Rn, maybe R3, we'll say 3 space, and we could just have that function be t of our 3 vector, x1, x2, x3, and it could just be the constant function 1 in the real space. M could be equal to 1 in this case. We're mapping from 3-dimensional space onto the real number line, and we just have the constant function. That would not cover the entire real number line, right? So the difference between the codomain and the range is that if we look here, the codomain of this, we map into the set of real numbers, R1, right? But our range, well, the only value that we hit is 1 in the real numbers, because for whatever reason we decided to define this transformation as the constant. So that's the difference between the codomain and range. The range of the values that the mapping actually attains on its image side, and the codomain is the set that we're mapping into. Some mappings cover everything and some don't. Okay, so matrix multiplication as a transformation. Of course, this ties into what we've been doing already. So we can define a transformation in terms of a matrix and matrix multiplication specifically by making the following declaration. If we have an m by n matrix A of real numbers, and then any vector in Rn, so x in Rn, we can define the transformation t of x as the matrix product of A times x. So we'll just multiply that vector by the matrix A, and then the result of that is the image or the output of the transformation t. Okay, so the second point here I'm going to come back to, but real quick, let's identify the domain and codomain of this transformation. Well, let's see. A is an m by n matrix. It's m by n. So we can only multiply it by a vector x, which is n by 1. So, and the result of that is going to be a vector, maybe I'll vector old friend y here for that. And that must be an m by 1 vector. Well, T then is a map, right? Because this is T of the vector x. We decided to define it as matrix multiplication of A times x. So it looks like T is mapping from taking a vector x that's an n by 1 vector, so it's in Rn, and we're mapping into, well, we're getting an m1 vector out of the product, which means we're mapping into the space Rm. So our domain is Rn, our codomain is Rm. So that handles the last question, or the last remark or question right here. Now the middle line, observe that the range of T is the set of all linear combinations of the columns of A. Okay, so the range of T, everything that T is able to map to is also the same as the set of all linear combinations of the columns of A. Well, let's think about this. T of x, right, is equal to A times x. And remember that A times x, if we rewrite this in its vector form, it looks like this. x1 times A1 plus x2 times the second column of A. Remember this notation from previous sections. And xn times the vector an. And when we look at that, we realize that, yeah, this is in fact a linear combination of the columns of A. Linear combination of columns of A. Okay, so if we're talking about the range of T, so the range of T, then what we're really talking about is all the x values that we could possibly plug into this, right, to see what we might get out on the other side, right? All the values that we can actually map to in the codomain side. So if this is true, which it is, we just wrote it down, this being the case, then what we're able to say is in the range of T is actually the span of the columns of the matrix A. And I'll just write that down in the column notation that we have. So it's all possible linear combinations of the columns of A. So probably the main point of talking about linear transformations now is that you'll see them later in practice or in other math classes potentially. And knowing that a linear transformation, which is something we're going to see shortly, is really just matrix multiplication, or that we can think about a lot of transformations, specifically linear transformations, in terms of a matrix transformation, really helps you keep a good understanding of what a transformation actually is. So let's have a look at an example then. We're given a matrix A of vector x and another vector b. Now these vectors are different dimensions, we kind of note that. And this matrix is, well, it's not a square matrix. It doesn't have the same number of columns as it does rows. So all these things should add up. We're asked to define the transformation T as matrix multiplication by A. Okay, so exactly what we saw on the previous page. They're asking us to say that T, the transformation of a vector x, is defined as the matrix product of A times x for any given vector x. Okay. We are given a specific vector x here, and we're going to do some calculations of that shortly. So first things first, they ask us to state the domain and codomain of T. So for part A, the domain and codomain of T. Well, let's be careful. If we're going to multiply something by, or A by a vector, this matrix A by a vector, we have to make sure that the number of columns in A matches the number of rows in the vector we multiply against. So it looks like, and that's the vector that we're acting on, right? So 2 columns in A, two rows in this X. So our domain is R2. Or the domain of T, we'll say, is R2, the plane or the two-dimensional real space. Okay, now similarly, what's the codomain? The codomain, improvising notation as we go here, just writing codomain parentheses. This makes sense. Codomain is equal to, now what's the output? We're going to do that for each row of A. We'll multiply by a vector. So it looks like we'd do that 3 times for the 3 rows of A, and we get results for each of the 3 rows. And that's going to leave us with a vector in R3. So the codomain of this is R3. If you're not sure, then try to make a matrix, try to take this matrix and multiply it by a vector of length 2 or 3 and see which one of those will work. And if whichever one does work, see which one you get an output for. But you could remember that A is a 3 by 2 matrix here. So it has to act on a 2 by 1 vector. And the result is going to be a 3 by 1. Just to keep that simple. So this one gives us the domain, and this one gives us the codomain, R2 and R3 respectively. But now let's get a little bit more specific here. They ask us to find T of X, and this is X as in this X vector right here. So keep that in mind. If it was a general X, we could do that as well, but what we would end up with is some X1 and X2, and we have an expression that involves those 2 variables. Now, A times X, this is just a matter of straightforward matrix multiplication. So I'll write my matrix down, and I'll write my vector X down. And remember, it's this row times this vector, entry by entry. So 2 times 1, 0 times -1. That's going to leave me with 2 in my first row. Second row does the second entry here, and it's times the vector column. So we have -1 times 1 and 1 times -1, and we get -2 out of this. And then 3, 1 times 1, -1. So we have +3 minus 1, and we get a 2. And that's it. That's the product of A and X in this case. So that would be T of X. Sorry, I could have been a little bit more clear, but we've already made that definition, just for emphasis. T, the transformation of X, is this matrix product of A against X, and that's the output. Let's see, find an X, so this is part C, find an X in the domain of T for which T of X is equal to B. Okay, so now we're looking for an unknown X value, not the same one we've already had. Notation's a little confusing. But what we're looking for is an unknown X that's equal to B. Well, we know what this vector B is. Let me write that in real quick. That is 5, -2, 3. Okay, remember X is unknown, but A is known. So let's fill in for A. When we do that, we've got 2, 0, -1, 1, 3, 1. And then X, our unknown, I'll just place that here. It's matrix times vector product, right? And then we've got 5, -2, 3. But remember, this is the matrix equation for a linear system, right? This vector X is technically X1, X2, if we wanted to fill in those details. So that makes this the X1 and this the X2 coefficient columns, and that would make this the right-hand side. So we could solve this. We could find an X value that maps a vector, or an X value for which A maps onto this vector right here. And the way we could do that is just form the augmented matrix of the system and put it in echelon form and solve for the system. So that's exactly what we'll do. But when we do that, what we find is, let's get it written down here. We find that when we make this augmented matrix, and I'll let the reader take care of the details here because this is just more practice with previous sections, 2, 0, 5, negative 1, 1, negative 2, 3, 1, 3, through, it looks like 3 row operations, we can arrive at something that looks like this. You may, if you just go to echelon form, you'll find something somewhat similar, possibly. The thing that's guaranteed is that you go to echelon form, what's guaranteed is the conclusion we're going to make from this anyway. You might have a different echelon form. Remember, echelon forms are not unique, but reduced echelon forms are unique. So every matrix has exactly one reduced echelon form, but it can have multiple echelon forms. So when we arrive at this, though, and whatever yours might look like, you should see that you have an inconsistent row in it, right? We have a zero, we have a leading entry in the rightmost column in this system. So we know we have an inconsistent system. And what that tells us is there's no solution to this. And what that says is, furthermore, there's no X value that maps to B, right? This is fine. This is right. The thing they actually asked us, they said, solve this equation. Is essentially what they asked. They said, find the X that makes this the case, that makes this true, that A times X is equal to that vector. Well, this is nothing different than what we've been doing before, solving linear systems. So, and what we found is that it's inconsistent. So that means that there is no X. There's no X such that AX equals B. And that's fine, right? We've seen that before. We've seen systems fail to have a solution. And in this case, what that translates to is it means that this transformation fails to map to this vector, right? And that's okay, right? It doesn't have to map to this vector. It maps into R3. It may or may not map to all vectors in R3. It turns out it doesn't map to this one. So some matrices or some transformations based on matrix products might map to every vector in the codomain. Okay, so part D. Part D asks us to, is there more than one X in the domain for which T of X equals B? Oh, well, this is sort of in conjunction with part C. Is there more than one X? Well, there wasn't even one X, right? So we'll just say no, there's not even one X, right? Now, how could there be more than one X that maps to B? Well, that would be the case of infinitely many solutions. If there was exactly one solution, in other words, if we had a leading entry here and here, and this was a row of zeros, well, that wouldn't be, well, no, that would be exactly correct. We'd have two leading entries, so both X1 and X2 would be basic variables. We'd have a row of zeros at the bottom, and we'd have a unique solution, because all variables would be basic variables. There'd be no free variables. However, another way it might work out is maybe we'd have a leading element here, and then this is a row of zeros, and this is a row of zeros. Right? And then we only have one leading element with two variables, and that would leave us with one free variable, which is X2, and that would leave us infinitely many solutions. But in our case, we didn't have any solution, so we can't have more than one solution. Zero. So part E, determine if the vector 2, 1, 0 is in the range of T. Okay, this is hardly different than what we did for part C, right? They're just asking it in a different way. If the vector 2, 1, 0 is in the range of T, well, if 2, 1, 0 is in the range of T, what they're really asking is there an X in R2, an element of R2, such that A of X is equal to the vector that they give us here, and that's 2, 1, 0. And well, it's the same game we just saw above, right? We wrote this situation down up here, and then we acted out through the augmented matrix and found that there weren't any solutions. So we do the same thing, but now we have 2, 1, 0 as our right-hand side, and see what you end up with here. I'll leave that one as an exercise, since it's no different than what we've already done. The interpreting what the question is asking is probably the more difficult part. So this example asks us to have a look at the effect that matrix transformations have on their domains. And we're doing that in a sort of simplistic way, and we're looking at how it transforms the 4 vertices of the unit square. That's the square that has points 0, 0, 0, 1, 1, 0, and 1, 1 in the 2-dimensional plane, right? So that's the points I just described are here, right? We have 0, 0 at the origin, 1, 1, and 0, 1, 1, 0. This is x1, x2, so all of our vectors are in x1, x2 form. And so off to the side, I did this matrix multiplication for this given matrix right here. A times 0, 0 gave us the 0 vector, 0, 0 once again. It looks like A maps 0, 1 to 3, 1, 1, 0 to 1, 0, and then 1, 1 to 4, 1. When we carry out all these matrix products, we'll get something like this. I spared the viewer the details because it's just straightforward matrix products. So 0, 0 maps to 0, 0. So if we look here, the red square is the original unit square that we're interested in. That's what we start with in the domain. What happens to this object when we apply this transformation to it? Well, this vertex stays the same. 0, 0 just maps to 0, 0 in the plane. So that's fine. And then 0, 1, that's this point on the y-axis here. 0, 1 maps to 3, 1. That's this point in black, right? So my domain element or object is in red, and then my codomain object, or my range object, I could say, is in black, right? The thing that the red square is transforming to this parallelogram. So this is we see what happens. 1, 0, 1, 0. This point remains fixed. It stays in place. And then last one, we have 1, 1 maps to 4, 1. So this point maps to this point. So this is called, I believe, a shear is what they call this. We've sort of slid the top of this unit square along the x1 direction, forming this parallelogram here. And we've extrapolated a bit, right? We didn't check whether or not these lines are actually mapping. We'd have to do intermediate points, but it turns out it is, right? It turns out this is the way it works. Or we could prove something about these linear transformations and how they preserve lines and things like that. But the point of this example is just to get an idea of what transformations do, what a matrix does. It takes points in space and it rearranges them in some sense, right? Now, it's not important to be able to visualize what a matrix transformation does for the most part. And in fact, really, it's only easy to see it in 2 dimensions, right? So if we have a 2x2 matrix, we can see what it does to its to the elements it might act on, you know, in its transformations domain. But beyond that, you know, a 3x3 matrix, 4x4. So 3x3 we can kind of envision on paper, and we can envision it at, you know, in space around us. It's hard to draw. 4x4, we're lost, right? We can't draw 4 dimensions. It's kind of hard to consider 4 dimensions. We don't live in that space. So we don't. This is just a brief look at what these transformations do. Don't get caught up too much in trying to know what every matrix does to every vector. Every now and then it's a useful thing to keep in mind. Now, further, going down to part B here, we have the matrix 1, 0, 0, 1. What does that do? Well, if you take a close look, and maybe you check this for yourself, if we multiply this matrix times the vector x, well, we just end up with the vector x. Right? Check it for yourself if you like. So it doesn't change any of the points. So the red square, the unit square, would just map to the same thing, the same object in the plane. I didn't even draw the plane for this one. I just gave us this little sort of graphic of the red square is just mapped right over to the black square. And they're exactly the same object, modulo my poor handwriting. So part C, what does part C do? A is a new matrix, 0, 1, I'm sorry, 0, 1, 1, 0. A little different from the previous one. the arrangement's off by a bit, and we see that it actually does do something different. 0, 0 maps to 0, 0. 0, 1 maps to 1, 0. That's where we see an actual effect happen. And then 1, 0 maps to 0, 1. If we, maybe you could plug in a couple more points if you wanted to, a couple other vectors, just to get an idea of how this thing's behaving. 1, 1 maps to 1, 1. What we see, which you'll eventually realize, is that this matrix reflects points around the x1 equals x2 line, or if we think about the old plane, that's the y equals x line. So it literally does a mirror image over this diagonal line. That's what we're seeing here. So the red square has this little single arrow identifier here. It's hard to see because the black square is drawn over it, and the red square has a double arrow identifier in this line. And if we think about these things being folded, remember that the point 0, 1 here maps to 1, 0. So 0, 1 is this point, and it gets mapped to 1, 0, which is this point. So this square is basically reflected over the line x1 equals x2. So this is a reflection type transformation. Other transformations that you might see potentially in the textbook is a rotational transformation, where we'd rotate this square around the origin. So shear, reflection, rotational, and I think translational. I don't know that. I don't think that's not a matrix transformation. So that is a rigid transformation, though, for another time. Now, linear transformations. Okay, so I mentioned this about transformations. The whole point of this is to discuss linear transformations, really. So let's get narrowed down into that. So if A is an m by n matrix, then the transformation T of x equals A times x. So defining the transformation as the matrix product A times x. Well, this transformation automatically inherits these properties. Remember that back in section 1.4, when we introduced the matrix operations, that A times U plus V is equal to AU plus AV. We can distribute the matrix across the sum. And similarly, for scalar products of vectors U, CU, we can factor the scalar out and write it in this form. Since that's the case, T, well, we would want T to inherit that. And if we define T as this, then we know that it absolutely will inherit it. But in general, since transformations don't have to be based on matrix multiplication, we can talk about a linear transformation. We have to define what a linear transformation is. We want it to have properties that are like this. So our definition is exactly that. We call a linear transformation, or T a linear transformation, if it satisfies T of U plus V is equal to T of U plus T of V, right? We can split the transformation across the sum inside. Now think back to functions, perhaps in calculus, right? Functions don't always do that, right? So keep that in mind. You know, a linear function will, but for good reason, because this is linear as well, right? But a function like, I don't know, f of x equals x squared, this function won't do that, right? This is a mistake. This is the old common Calc 2 or college algebra mistake, right? If I have f of 1 plus 3, it's not equal to 1 squared plus 3 squared. It's not equal to f of 1 plus f of 3, right? It's because f of 4, well, that's 16 in real life, but over here, we'll ask, is it equal to 10? 1 plus 3 squared? No, not at all, right? So this is not obeying that property. That's an example of a nonlinear transformation. So that kind of motivates why we define a linear transformation. So the other property is the fact that we can factor out scalars, just like this line was suggesting we would want. And that's in fact the case. So if we're given a T is a linear transformation, then the transformation of 0 is equal to 0. So the 0 vector maps to the 0 vector of the codomain space. Let me give a quick proof of that down below. We've got another part of this theorem, but think about it this way. T of 0 remember that the 0 vector plus the 0 vector is equal to the 0 vector. So I've expanded my argument inside T, expanded T's argument here. And then I know that T is linear, right? We assume T is a linear transformation. So I can split it in this fashion. I can split over the sum inside of its argument because it's linear. So then I have T of 0 plus T of 0. Well, all of that is still equal to the 1T of 0. So I have 1T of 0 is equal to 2T of 0. And the only way that can be true is if T of 0 is 0, right? T of 0 is anything that's not 0, then I'm going to have a contradiction in that. So we're able to prove that pretty quickly from the linearity property. Now the other property follows pretty straightforward from the definition. It's just really a matter of applying both of these at different times. But T of a constant times U plus a constant times V, CU plus DV is equal to, you can split the sum and factor the constants out. So other linear transformations that we might consider, or maybe linear operation, I should say, would be the derivative in the integral, right? Remember, derivatives and integrals have this property. If you're integrating a constant times a function plus a constant times another function, you could split up the integral as the sum of two integrals, and you could factor the constants out. So linearity is a really common thing in mathematics. It's a very useful tool. It's nice to be able to split those integrals up back in calculus, and it's going to be nice to be able to use linear transformations in that similar fashion. So our last example is for a transformation from R2 to R2. We're going to define it as T of X is equal to -3 times X. All right, that's a pretty basic transformation. It's just a scalar product with the vector, right? So that's not too bad. They ask us to show that T is a linear transformation. All right, so we have to show two properties. We have to show, so we must show that T of X plus Y, two different vectors, right, is equal to T of X plus T of Y. All right, so we'll get to that. And the second thing we need to show is that T of a constant times the vector X is equal to C times the transformation of the vector X. So in other words, we can factor the scalar out. So in order to prove these things or to show these things, we just have to write down what T is. For part one, we'll do this. We'll say that T of X plus Y. Well, remember, this is a single vector, X plus Y. So what happens to it is we have -3 times the vector X plus Y. Now we rely on vector properties. We know that a scalar times the sum of two vectors obeys this property. If we go back to, I believe, section 1.3, where we can see this property of vectors, this is why we had that whole table of properties for vector multiplication or scalar multiplication of a vector, and so on. So we can do this. And when we look closely, we realize that, oh, this is actually what T is defined as. T of X is -3X, or T of Y is -3Y. So we can rewrite this as T of X plus T of Y. Because -3Y is T of Y and -3X is T of X. So we have this properties confirmed or shown, demonstrated, we'll say. Now the second property for a constant, let's C be a real number. Be very thorough about this. Any real number scalar. I guess we should have let X and Y be elements in the domain of T, but this is fine. Let C be an R. So then T of C times X. Remember that C times X is still a vector. So there's not really much going on with this. We just end up with -3 times C times the vector X, or -3 times the vector C times X, right? And since this is a constant and this is a constant, we can rearrange them. We can put a C out here times -3 times X inside. And then we realize inside the parentheses is just T of X. And we have exactly what we're looking for here. This thing passes constants through it, so we're just fine. Good. So both properties check out, and that's the basic way to, and that's our simple demonstration for showing that something's linear. It's always two properties. Show that it splits sums and preserves them, right? And show that it factors out constants. Good, so that's the introduction to linear transformations. We'll develop some properties of those in the next section. These are, again, important things in mathematics and mathematical application, so it's well worth the time we're going to spend on it.